Welcome back, everybody. As a reminder, homework for 2.5 was extended along with quiz until this Sunday. I have updated the home pages. I didn't get to it until yesterday afternoon because my son was sick. But as you can all thank Hector for this, he was the one who suggested it. But I'm going to open up later today. I'm going to open up all the old assignments for Unit 2 material. If you've already done it, kudos to you. You should just focus on the exam review and stuff like that. But I want to make sure that it's a win-win for me. It's a win-win if I open up the homework assignments because it's winning for you guys because if you do it, then you get more points and you're studying, and it's a win for me because then you're studying more. I'll be updating that sometime later today when I get a chance. But we have to go through the last minute material for Unit 2. And so going back over this whole thing before we get started, because I do want to mention something about it. So the domain is where the denominator equals 0. And that also somewhat corresponds to the vertical asymptotes and the holes. But we'll talk about that in a second. So whenever I see one of these problems, I always want to write it in its unfactored form, its factored form, and its simplified factored form, because all three of those formats give me different bits of information. And some are more useful in other situations than others. The factored form is far more useful for finding domain than the unfactored form. When it comes to intercepts, the factored form, granted, we didn't need to factor anything in the numerator, but the factored form helps us find the x-intercepts easier. But the unfactored form is much faster at finding the y-intercept, because instead of having to plug it in 3 different places and multiply them together, I can just replace all the x's with zeros, because if I'm placing a 0 in for the x, that whole term gets wiped away. Then we come to the asymptotes. Vertical asymptotes and holes come from the denominator, pretty much. If a factor gets completely wiped out, there's going to be a hole, and then the new denominator, which in this case was the same as the old denominator because nothing canceled out. You set that equal to 0, and that gives you the vertical asymptotes. And that's why the factored form is very useful for it. And then for the horizontal asymptotes, it's best to look at it in its unfactored form, because you're looking at the degree of the numerator versus the degree of the denominator. Now, here's the thing where Alex wants you to get involved, but I'm going to show you in Unit 2.6 a way to do it without plugging in numbers. But this is what Alex did, and this is still fine, by the way. If this problem shows up on an exam and you want to graph it, if you just want to learn this method and utilize your calculator, more power to you. Just plug in several numbers in between each thing, and because our calculator has a store feature, you can just replace all the numbers very quickly to get the answers. And as we talked about last time, though, most of the time these numbers will be fractions. And so when that happens, for us, we can use the approximations to roughly guesstimate where it's going to be. But on Alex, you want to make sure you write them perfectly as fractions. Otherwise, it won't do it properly because it'll be trying to plot an approximation when it really needs the exact value. Does that make sense? Any questions on that? Okay. So graph this rational function. We've got 4x squared plus 16x minus 20 over x squared plus 7x plus 10. So first things first, we're going to write down all the bits of information. We're going to factor it. And in the numerator, you might notice that there's a common factor of 4. And so that would leave us with an x squared plus a 4x minus a 5 divided by the denominator. We could factor it right now if we wanted to. But I'm going to hold off for the next step. So I'd like you guys to go ahead and factor that, practice your factoring. We're going to be doing a lot of that today once we get to 2.6. So I'm going to pause the recording while people watching the recording, you should also factor right now. So that's way too loud for the recording in progress part. Anyways, so we should get this. It does factor to 4 times x plus 5 times x minus 1. You want to find 2 numbers that multiply to -5, and the same 2 numbers need to add to 4. That would be 5 and -1. Similarly for the denominator, and therefore the x plus 5s cancel out. And since the x plus 5s completely cancel out, that means that there's going to be a hole where that factor equals 0. So x plus 5 equaling 0 means that you have a hole at x equals -5. So that's our new denominator. So the domain comes from you need x squared plus 7x plus 10 to not equal 0, which we already factored to x plus 2 times x plus 5 cannot equal 0. So that gives us that x cannot equal -2 and -5. And I think we've seen enough of these so that we don't need to draw the number line anymore. But if you still need to do that, go right ahead. But the domain is therefore parenthesis -infinity to -5 per n parenthesis union -5 to -2 parenthesis union parenthesis -2 to positive infinity. It might be tempting to just look at the simplified denominator to say, oh, it only doesn't exist at -2. But remember, when you cancel out a factor, it means that provided x does not equal -5. So that still plays a role. The simplified version is just for vertical asymptotes, basically, and that's it. Yes.
I think you just said this because when I was doing the homework, I was having a hard time with like the numerator part as to like how would it go about like writing it down like in this.
Gotcha.
Does it include it in any way, or is it just assumed because it's between -5 and -2? Or
Sorry, say that one more time.
never mind, I take that back. But is it just assumed that it's included in there, or
The -5.
the numerator?
Then when we're finding the domain.
Yeah.
So the numerator doesn't play a role in domain at all, because the numerator can be 0. That's not a problem. Having 0 in the numerator is fine, right? Because 0 divided by 5 is still 0. 0 divided by -1/10, that's still 0. It's when you divide by 0, that's the issue. Because any number divided by 0 causes problems. It either becomes undefined if it's a non-zero number, like 5 divided by 0 is undefined, or it becomes indeterminate when it becomes 0 over 0. And those are both problems. So it's only dividing by 0 that plays a role with domain, because 0 in the numerator is not the issue. So that's our domain, and then our x-intercepts. Now you because it shouldn't be in the domain when you cancel that out, you can kind of skip it, but I'm just going to do it anyways and write that you need to make the numerator equal to 0. So 4 times x plus 5 times x minus 1 has to equal 0. And once again, the reason for this is not anything new. When it comes to x-intercepts, you're setting y equal to 0. That is, you're setting the function equal to 0. But the only way the function, like if this is 0 here, the only way that happens is if the numerator is equal to 0. So that's why we're just skipping the middleman and immediately just setting the numerator equal to 0, because that's the only way for it to possibly equal 0. And that gives me x equals -5 and +1, but this is not in the domain. So we just have 1, 0. One, 0 only. There were 2 potential spots for x-intercepts, but one of them is not in the domain, so it's not an x-intercept.
But how can that not in the domain?
Because it was also in the denominator. When you plug in -5, you get 0 over 0, which is indeterminate. And so that's going to give us a hole, but not an x-intercept.
So that's why it's.
Yes, exactly. Exactly. I mean, I hate to be a Starbucks barista. It's not because it's undefined, it's because it's indeterminate. It's so stupid. I know it's grande, medium kind of mean the same, or venti and large mean the same thing, right?
Similar concept, but like
Very, very closely related.
Oh, okay.
Very closely related, but one can be a value given context. Undefined is never defined.
Okay.
Indeterminate is something that is not determinable unless you're given context to figure out what it should be,
All right.
which is what we've been we did that right in this problem, right?
Context when I can't be used in context.
Exactly right. this was an example of that because in the context of this problem, yes, one is going to be indeterminate. It can't be plugged in, but if it could be plugged in, it would give us 5. So that, and sadly, the thing I wish I could say more, I wish we could talk about it in more in detail, but it requires the concept of limits, which is something we deal with in calculus, which we won't see for another 2 semesters. So calculus is very, very fun. Like I really, really like that course. It's a very, very fun one. No, 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 no. My wife thinks it's a fun course. So that's 2. That's 2 right there.
Dude, that calculus is like fun. This is just like
It-
part of it.
One of the things that's really nice about it, so this is a thing in mathematics that you will see time and time throughout your career in mathematics, is that there's kind of a hazing process. You have to do it the hard way so that you can appreciate the easy way. And pre-calculus does a lot of the hard work. Pre-calculus, a lot of, and algebra too, whereas in calculus, a lot of the algebra stuff, it's important, it's right there, but you get to bypass all the things that were frustrating in pre-calculus. So that's one of the reasons why I like it a lot. I remember in grad school, I think I've told this story, but I had to prove that the sphere was a surface. I had to prove that it was based on the mathematical definition, and that took 4 pages. And then once I turned in that paper, my teacher said, okay, now that we can assume that's true, we'll just assume that it's true always. And then we don't need to do that ever again.
Well, it's true, because look at the Earth.
Well, yes, but like specifically from a mathematical definition of what a surface is, it's a very, very convoluted definition, but regardless, proving it requires you to show 80 million different things. It's very, very annoying. But then once we did that, he was like, okay, so now whenever we see a new surface, we'll just claim it's a surface. We don't need to go through and prove it. And I was very, very upset at it, but that's part of mathematics, is having to do it the hard way so you can appreciate the easy way. Okay. Y-intercepts. Same, like usual, you're plugging in 0 for x. When you're finding an intercept, you set the opposite variable equal to 0. So in this case, we're setting x equal to 0, but that's the same thing as computing the function at 0. And I can use any of the calculations here. I can use this one, this one, this one, or this one to plug in 0, because 0 is in the domain. But I would recommend using this one because all the things will become 0 except for the constants. So y of 0 will be 0 plus 0 minus 20 over 0 plus 0 plus 10. That'll give me negative 2. So I have 0 comma negative 2 on my graph. Once again, Alex will want it as just negative 2, but I want you to recognize that it's also a coordinate point with an x value of 0 and a y value of negative 2. You plugged in 0 for x and got a y value of negative 2. That's why we have the point 0 comma negative 2. Next, we need to find our asymptotes and our holes, and then we'll be ready to graph, and then some test points throughout. So, holes. There's one at x equals negative 5, and we'll plug in it into the simplified version because that is what the curve should look like at negative 5 if we were able to plug in negative 5. So that is, we're going to plug in 4 times negative 5 minus 1 over negative 5 plus 2. And that will give me negative 24 divided by negative 3. That's positive 8. So we have negative 5 comma positive 8 as our whole. Yes, Connor.
Do we only care about the negative 2 being in that x? Because it says it could.
Yeah.
be
Oh,
the-
good. Yes. Sorry, I interrupted your question because it's a great question. And I was hoping someone would ask it. So we only ignore the negative 2 in the case where it's an x value. This is a y value. The y values can be whatever we want. That's fine. It's just the x values can't be negative 2. Then we've got vertical asymptotes, VAs. And this is where the new denominator equals 0. So that is x plus 2 equals 0, which gives me x equals -2. I'm going to underline all these bits and pieces of information because they're all relevant. But we have a vertical asymptote where the new denominator equals 0, which would be just at -2. And then, last thing to find, other than some extra test points, is to find the horizontal asymptote. And this is a cool thing that you can use to remember this, by the way, is remember, end behavior for polynomials, we had to look at the unfactored form. The same is true for rational functions. To look at the end behavior, we'll look at the unfactored form. They're both degree 2. So for the HA, degree of the numerator equals the degree of the denominator. Now, you don't have to write that. On an exam, you can just claim that the horizontal asymptote is y equals 4. The idea being that these things are going to increase at the exact same rate. The other stuff around here, the 16x minus 20 and the 7x plus 10, they don't mean squat in the face of infinity. So what's happening here is when we plug in a billion, the other stuff basically is negligible. So it's 4 times a billion squared over 1 billion squared. The billion squareds cancel, and you just have 4 over 1. No matter where you plug, like no matter how big of a number you get, it's always going to be 4 times that number squared over that number squared. The squareds cancel, and you just get 4 over 1. So the degree of the numerator is equal to the degree of the denominator, which means we have a horizontal asymptote at y equals 4 over 1, which is just 4. Yes, it is. Okie dokie. So let's go ahead and plot all the information that we have and see if we need more. So we have a vertical asymptote at -2. And you don't necessarily need to, I just realized you don't necessarily need to draw the arrows on the horizontal asymptote because it's not actually there. If you ever graph this in Desmos or in a graphing calculator, they never draw the horizontal asymptote. It's there for us to know what it looks like and how to draw it. But at the end of the day, it's not needed. And then for a horizontal asymptote at 4, and then let's plot all of our little points that we got. We got an x-intercept of 1, 0. That's right there. We got a y-intercept of 0, -2. And we got a hole at -5, +8 right there. So, looking at this, and I know I said that a function can cross through its horizontal asymptotes locally, but that's pretty rare for that to happen. So usually it never, like, it's very, very rare that the function would go like this. That's not very common. So more likely it's going to go like that. But anyways, so don't worry about trying to like make it look fancy or whatever, or trying to make it look cool. It's mostly just going to be very, very uniform. So we have 2 points on the right-hand side of the x-intercept. We should probably, even though we have a hole, the hole doesn't quote unquote correspond to a point on the graph. So we probably need to do some calculations on the side. So y of, let's say, -6, which is going to equal, let's use a calculator because I don't want to calculate that by hand. Though that being said, remember that these two versions, here's a little quick trick. Remember, these are all equal. So I could, in fact, use this version of the formula. It'll be faster. It's not wrong to use this formula. It's not wrong, but this one's faster. So 4 times -6 minus 1 divided by -6 plus 2 gives me 7. That doesn't seem right. Because that should be, oh, no, that's fine. That's fine. So there's a point right there. And we could probably find another one. Maybe we could do -4 or -3. Let's do y of -4. And that will equal, if I change those to -4s, I get 10. So I have this point right up here at 10 right there. And it's going off the screen a little bit. Sorry about that. But the idea is still the same. Now, 2 should be enough for us to figure this out. If Alex wants more, just plot a few more. It's not going to be too terrible to get it all squared away, but that's enough for us to figure out what this graph should look like. It should kind of go down to here, and it should go up like that. And then here, it's not going to magically come down like that. That is so rare, and that requires a very convoluted looking rational function that we don't have. That's usually one that happens when you have like x to the 5th situation, and it's like this big mess of things that's going on. So instead, go with the path of least resistance, which should be like this. Are there any questions on that?
Okay, so it's also where there's parts where other topics where you say -6 and -4, you have to plug in there's certain parts of the line. How do you know which numbers exactly?
I pick them kind of wherever I feel like. As long as they're on one side, like basically I pick about 2 to 3 points in between, like on each segment that's divided by a horizontal, a vertical asymptote.
So if it's like in the negative, it's going to use negative numbers.
Yes.
But sometimes it will use positive.
So because there's 2 halves to this thing. So I want about 2 numbers on this half, 2 to 3 numbers on this half, 2 to 3 numbers on this half. For my exam, I only really need you to plot the x-intercept, y-intercept, and any holes, because I'm going to show you in 2.6 a way that you can bypass plugging in numbers. Yes, come.
When you're plugging the y, like -4 and then -6, what formula are you plugging that into?
So, excellent question. Connor's asking, when I'm plugging in -6 or -4, which formula up above am I plugging it into? I can plug it into any of them. They're all equal. The only places where they're not equal is at -5, because that's a situation where you get 0 over 0 in this, and I get 8 in this, because that's what it should be if we could plug it in. So I can use any of the formulas because they're all equal to each other. And as long as I'm not plugging in -5 or -2, they'll always give me the same number. So I used this version because it was faster, but granted, in your calculator, it can compute this just as fast as it can compute this. It just takes about maybe 2 extra seconds to plug in the numbers because you have to do 2 more situations. But it's not like any of them would be fine.
Okay.
All right.
If you were to plug it in like past on the positive side,
Mhm.
it would be X, right?
Yeah.
It wouldn't go over.
No, it wouldn't go over its horizontal asymptote. That like what I can tell you is it's possible for that to happen, but in this course, you'll never see it. That's like, I just want you to know that like the main reason why I presented that is just to talk about the fact that horizontal asymptotes, they deal with end behavior. They don't care what's happening locally. They really don't care about this line locally, but almost every situation we will see, it'll never be the case that it jumps over and then goes and then levels off. That's very rare. All right. Any other questions?
So when doing those -6 and -4, you know, just the lines like when it shows on the graph says -6 and -4 to do those points.
Yep. Yeah, and just you like, like on these ones, sometimes you luck out and you get nice integer numbers like 7 and 10 with -6 and -4 respectively. But a lot of times it's something like when you plug in -6, you'll get a y value of like 14/7 or no, 14/71 or something like that. Something nasty.
It gets a lot of like fractions.
Exactly. And that's why that plotting point feature, this one like that goes like that looks like that. That's going to be your bread and butter for these ones. Use that feature because trying to find 14/71 on a graphing grid is not feasible.
And if you, let's say, find a decimal answer, it says do not use a decimal answer because that's a very.
Because that's going to be an approximation. So like if the answer is 1/3 and you use 0.33, that's going to be off by 0.03003 repeating from the actual value. Any other questions? Okay. The next one is negative x squared plus 2x plus 3 over x minus 1. So whenever I see my leading term being negative, I always want to factor out the -1 just to make it easier for me to factor. If you don't want to do that, you're not required to, but it really helps me out. So I'm going to factor out a negative, and then this becomes positive x squared minus 2x minus 3 over x minus 1, and that will factor nicely to x minus 3 times x plus 1 over x minus 1. And notice that nothing cancels. The x plus 1 and the x minus 1, they're different factors. They don't cancel. And we can't cancel the 1s, we can't cancel the x's there because they're terms. You can't cancel the x's because this is a term inside this factor and this is a term down here. You can't cancel those. So we leave it as is. Nothing cancels, so there's no holes. Ali, did you have a question?
Yeah.
Yeah.
This is kind of something I was having a hard time with in general, but
Mhm.
you know that like thing where you can make like looking at x minus 1, you could technically put it outside of the parentheses like a negative and then make it x minus 1.
Okay, yeah.
When do you know when you apply that? Like
So if you see your when to factor out a -1 from like if you have x minus 6 over 6 minus x, like that's what you're referring to. So this is the primary situation that I see it. If my variable is not first, that's a good indication to me to try and factor out a -1. That's usually when I use this.
okay.
Or so if the numbers are exactly the same, but the signs are different, I will always try it. So if it's negative x plus 6, I'll try and factor out a -1 because they both have a 1x, they both have a 6. Maybe I can factor out a -1 and it'll work out. Maybe it does, maybe it doesn't. I'd still try it if it was like this. I'd still try it because I see the negative x, I see a 6. Maybe it'll work out. It won't, because if I factor out a -1 from this becomes -1 times x plus 6, and it won't cancel with that. But it was worth a shot. So whenever I see the same numbers in the same x variable, I try to factor out a -1 to see if it'll cancel. Otherwise, I won't bother. So nothing canceled, so there's no holes in this graph. But now, well, what we'll do is we will find the domain, find the x-intercepts, all that stuff. Domain, the only thing we need to worry about is the denominator because we can't divide by 0. So x cannot equal 1. So that gives me the domain -infinity to 1, parenthesis, union, parenthesis, 1 to positive infinity. Feel free to draw the number line if that helps you out. I want you to find the x-intercepts and the y-intercepts if they exist. People watch the recording, do that right now, and then when you're finished, just resume the recording. All right, so you should get 3, 0 and -1, 0 for your x-intercepts by setting the numerator equal to 0, which happens once again. I know I sound like a broken record, but I just want to keep reminding us that an x-intercept, you set y equal to 0, so you're setting the function value equal to 0, but the only way that could happen is if the numerator equals 0. So we're just skipping a middleman. We're skipping that one extra step of setting the whole function equal to 0 because we know the only way it could happen is if the numerator equals 0. And you get 3, 0, -1, 0. And then for the y-intercept, you're going to set x equal to 0, but that means plugging in 0 into the function, which gives you -3. So we have the point 0, -3. Then the last thing to do is to find the asymptotes and the holes. There is no hole. So I'm just going to say holes, none, smiley face, VAs. Now this one has only one vertical asymptote because we're going to set the new denominator equal to 0, even though it's being hidden right now. The new denominator is the same as the old denominator because nothing canceled, but that's okay. Just set x minus 1 equal to 0. which gives us x equals 1. And then horizontal asymptotes. Is there a horizontal asymptote? Looking at the degrees, the numerator is degree 2 and the denominator is degree 1. So when you're talking about end behavior, the numerator is going to blow up much faster than the denominator because it's got an x squared, whereas the denominator only has an x to the first power. So as x gets larger and larger and larger, the numerator is going to get bigger way faster than the denominator, and the denominator won't be able to keep up, so it'll blow up to infinity. It will never become a finite number. So it does not have any horizontal asymptote. But does anybody notice anything? So there's no HA, but there is a different type of asymptote. There's an oblique or a slant asymptote because the degree of the numerator is 1 larger. That's the one weird case. We talked about it last time, and it was that if you have that the degree of the numerator is exactly 1 more. So if you have like x to the 4th over x cubed or x to the 10th over x to the 9th, most commonly it's x squared over x or x cubed over x squared. Those are the most common situations we see. But if you have that, then there is an oblique asymptote, and you find the equation of that oblique asymptote by performing the division, because degree of the numerator exactly 1 more. So we'll find it up here. Now, because we're dividing by x minus 1, we can use synthetic division. It's not wrong to use long division, regular polynomial long division, and you're more than welcome to do that. If you don't want to learn synthetic, that's your choice. But I would try and use synthetic wherever possible. So our C value here is 1 because you can only use synthetic division if you're dividing by x minus C. This is already in the perfect format. It's in the form x minus 1. So our C value is 1. We'll set up the synthetic. So negative 1x squared plus 2x plus 3. And luckily for us, all powers of x are present. So bring down the first one. And then for the rest of it, you're going to multiply diagonally, add vertically. 1 times negative 1 is negative 1. Add that. You get positive 1. 1 times 1 is 1, which gives us a remainder of 4. The quotient gives us our oblique asymptote. So we have an OA at y equals negative x plus 1. Negative 1x plus 1. I guess I'll make that concession for a second. You should just write negative x, but I want to make sure it's very clear that this is from the quotient. Negative 1x plus 1. So we have everything we need. We might need to plug in some more points for Alex's sake, but we'll see what we need to do. We'll plot everything we have. We know we have a vertical asymptote at x equals 1. So let's graph that. Then we know we have a slant asymptote or an oblique asymptote at negative x plus 1. That's aligned with y-intercept 1. Let's go ahead and plot that. Y-intercept 1, and it has a slope of negative 1. So you can either go down 1, right 1, or you can go up 1, left 1. It doesn't matter what you do. I'm going to go down 1, right 1, like that. And then I just carry out the line as best as I can. That, and that will do it.
How'd you know where it was pointing?
From the slope. Like, how do I know where to go? Yes, from the slope. Since it's a slope of negative 1, that's a rise of negative 1 over a run of 1. Or you can think of it as a rise of positive 1 over a run of negative 1. So you can either go down one, right one, or you can go up one, left one. No matter how you choose it, though, it'll be fine. And so now we got to plot all those points. We had the point, we had an x-intercept at 3, 0, so right there. We had an x-intercept at -1, 0, and we had a y-intercept at 0, -3. So we have 2 points on the left half of one of our vertical on the left half of a vertical asymptote. We should probably have one more on the right-hand side. We only have one. So let's do f of 2. F of 2 would be equal to, let's use our calculator. So fraction negative parentheses 2 squared plus 2 parentheses 2 plus 3 over parentheses 2 minus 1. I'm putting parentheses around all my like my inputs because I might need to plot more points, and it's easier if they're in parentheses. That way you know exactly where they are in the expression, and you know where to where to delete. And it also makes sure that you don't make any mistakes with minus signs, because if you just write in your calculator, if you just write -2 squared instead of -2 quantity squared, it will read that and give you -4 when you should get +4. So anyways, we plug in 2, we will get 3. We lucked out and got another nice integer number. So 2, 3 right there. And that's probably enough for me to graph this. So we need to go through those points. So it doesn't make any sense for us to be up here. Because remember, functions need to, irrational functions, they hug their asymptotes. So it's either like that or it's like this. Which one's more likely, pink or blue?
Pink.
Pink, because pink actually goes through the points. Blue does not. Like, in order to make it blue work, it would have to look very, very strange. It would have to go like, and that doesn't really look very, very normal. And these things normally look very, very normal.
I'm sorry, what you mean?
The 2, I wanted to plug in a number that was on the right-hand side of our vertical asymptote. I only had 1 as it stood. I only had 3, 0. So I wanted to do one more. There was nothing. Oh, go ahead.
Pattern.
Yeah.
3 rise, 3 300, 3 over. So you just look at the other pattern on the left. Okay, you just translate the same thing to the right.
I mean, I could have, there's nothing stopping me from doing 1.5 or 8.758. I could do that. It wouldn't be wrong to do that, but it would just be usually work with the smaller numbers. The smaller numbers are. Say what?
If you do the other thing, it'll be wrong.
They want it to be a very, very specific ratio.
In a way, kind of like that.
Okay. I suppose they want them to be very, very close to the x-intercept, so you know this is not the x-intercept, the vertical asymptote, so you know exactly the behavior that's happening.
What I'm saying is that since the one on the left is go down 3, go, then you run to the next one. You did the exact same thing.
Oh.
Just like upside.
That is more of a coincidence than anything.
Oh.
That's more of a coincidence. And so we have everything we need. We've got to hug our asymptotes. So it should come down, and it does not need to be perfect, but that should be enough. And then the other one, it has to go through those 2 points. So it should end up looking like, oh, sorry. I accidentally pressed the home button. Should look like that. And that is our graph. Are there any questions on that? Yes, Shane.
Does the remainder from the synthetic division affect anything?
No, it does play a role, and it's for illustrative purposes to understand, but in terms of the graph, it has no bearing. The real reason it's important is to understand what happens. So -x² plus 2x plus 3 divided by x minus 1. By the division algorithm and performing our division, it's equal to -x plus 1 plus our remainder divided by our divisor. And the whole point of why we get slant asymptotes is that at infinity, We can't plug in infinite, but if we could, it would mean that this would be basically zero, right? Because if you plug in 5 billion, you're going to get 4 divided by 4,999,000 or 999,999,999. And that's basically zero. So when it comes to really large numbers, our function basically looks like negative x plus 1. That's where the remainder comes into play. But that's it. It doesn't do anything when it comes to graphing it. It's for merely the understanding of how slight asymptote occurs. Great question. Good? Oh, Darren.
So, roughly, where did you get the points from?
The points, all the black points on the graph. So 3 of the points came from the x-intercepts and the y-intercept, 3 comma 0, negative 1 comma 0, and 0 comma negative 3. And I wanted one more point, so I just plugged in a number 2, but I could have just as easily done f of 5 or f of 4 or f of 10 or whatever, but I just chose f of 2. Try to choose smaller numbers. They're easier to work with. You could all like, there's nothing stopping you from instead doing f of 4 to plot another point. And Alex should be okay with 2, but it might need more, and in which case then we'd probably do f of 4 and maybe f of negative 2 and call it good. One more point on each side of the vertical asymptote. Cool?
With the pink purple line, for the OA.
Mhm.
The points, I can see that it's like negative 1 and 1, and I see that it's on like that y equals negative x plus 1. But I guess I'm not understanding exactly like how you get,
How did I create it?
not create it, but like negative 1 is gonna be like, how do you get to the points after you've already gotten the equation?
So these 2 points here?
Yes.
So I'm using my knowledge that this is a line. So the 1 here is its y-intercept. So I know it goes to the point 0 comma 1. And then this is the slope, which is the rise over the run. So because it's negative 1, that's a rise of negative 1 over a run of positive 1. So that's down 1, right 1. You could also go up 1, left 1 if you wanted to, but it's fine either way. Convention is to move to the right. So that's what I did. Cool. All right. Any questions on that? Okay. That's a good stopping point for our first break, so we can get started with 2.6 afterwards. Let's come back at 10:28. People watch the recording, go do some push-ups. Okay, so one of the most useful aspects of polynomial, like of this course, in my opinion, has to do with nonlinear inequalities. Specifically, one of the things that we're going to be doing in this section, which is a sign chart. They are very, very useful. You use them all the time in Calc 1, so it's very, very useful to be good with them. And they also have a really, really good implication graphically. So our goal is to determine where nonlinear functions, mostly polynomials and rational functions, but it can be generalized later on, where they are positive, i.e. above the x-axis, or where they are negative, below the x-axis, without the use of a graphing tool. So solve the inequality x minus 5 times x plus 2 squared is less than 0. Okay. So this can't be solved like a normal linear inequality, like a linear inequality. If we have 3x minus 5 is greater than 0, we can use the properties of algebra to bring the 5 over and then divide by 3, and that won't change anything, and that'll be fine. But much like the same analog with linear equations versus nonlinear equations, we have to do something different. And so with inequalities, with nonlinear inequalities, it's all about factoring again, because we're going to kind of use the zero product rule in essence. So step 1 is you're going to move everything to one side and combine and then factor as much as possible. One side of your inequality should always be 0 in this case, just like with the polynomial equation. When we solve polynomial equations, we bring everything to one side and set the other side and have the other side be 0. So in this example, that's already done for us. Smiley face. Then what you're going to do is you're going to set every factor everywhere. There is no denominator here, but we factor the denominator as well, and we'd set all of the factors equal to 0. And then I'm going to call those my VIPs, my very important points. I'm very clever, I know. And then you might be, I know there's going to be one student out there being like, but Phil, they're not points, they're values, because it's an X value. It's not a point. A point has two spots in it. It's a coordinate point. And my response to that is, I know, I'm aware of that fact, but Viv doesn't have the same ring to it, right? Very important value. It doesn't have the same thing as a VIP. So if a VIP makes the denominator equal to 0, underline it, highlight it, something, and call that a problematic VIP. We'll discover those more when we have an example. But in this situation, so we have x minus 5 equal to 0, which gives us x equals 5. And then x plus 2 equals to 0, which gives us negative 2. Those are my VIPs. And we're writing this for our note-taking purposes. We don't need to mention this in practice. None of these are problematic VIPs because there is no denominator equaling 0. This is a polynomial inequality, and we don't have any denominators with variables in a polynomial. So none of those are problematic yet. We'll see some examples in a second. Now, you're going to set up a sign chart using the values you found in step 2. Circle, highlight, underline, box in any of your problematic VIPs to remember that you cannot include them. Once again, that'll make more sense once we get there. So, how do we make a sign chart? I'm going to rewrite the inequality, but I'm going to write it in color. So it was x minus 5 times x plus 2 quantity squared is greater than 0. And why this works, I will happily go into in just a moment. So you're going to make a number line, and then you're going to make 2 vertical bars. And so our VIPs were negative 2 and 5. So put them on the number line in the proper order. So negative 2 is the first one. And here's 5. And since I'm trying to solve for where this is positive or where maybe I could also have less than 0 in certain circumstances, all I really care about then is the sign. If the overall sign is positive, the result is positive. And I don't need to know what it is. I just need to make sure that it's greater than 0. So really, at the end of the day, I could plug in test value. And what I'm going to do, sorry, I'm getting ahead of myself. These 2 vertical lines have divided the number line into 3 segments. There's the negative infinity to negative 2 piece, the negative 2 to 5 piece, and the 5 to positive infinity piece. I want you to pick any random number that you want inside each of those segments. So for the first segment, I'll choose x equals negative 3, but you could troll me and write negative 30,000 or something like that if you want. But any number will work that is less than negative 2. Then in between negative 2 and 5, if you have the opportunity, always choose 0 or 1 or negative 1. So I'm going to choose 0 here. And x equals 6. These are test values. Yes. Scroll up just a little bit. Yes. So what I'm going to do with these test values is I'm going to plug them into the inequality and see if they solve it. Now, I could go through and plug it in and figure out the exact value. So if I plug in negative 3, that's negative 8 times negative 3 plus 2, that's negative 1 squared, that's positive 1. So it's negative 8. I can do that. And that's a negative number, so the resultant is negative, and that's not going to solve the inequality. But at the end of the day, all I care about is the sign. Because if it's positive, then it's a part that I want. If it's negative, it's going to be a piece that I don't want. So what I'm going to do is with the factored version, I'm going to just worry about the sign. Negative 3 minus 5, that's going to be negative. So the reason why I've color coded it is to say that factor will be negative there. -3 plus 2, that's negative, but it's being squared, so that results in a net positive. So a negative times a positive, that is a net negative. And that is not a piece that I want, or we'll get to that in a second. So the expression x minus 5 times x plus 2 squared is negative here. Suspend your disbelief on why that's true. I'll explain in just a moment. Then we'll test 0. 0 minus 5, the red piece, that's going to be negative. And then 0 plus 2, that's going to be positive. That's squared, so it stays positive. So this piece is positive again. And it'll be negative here, a net negative. A negative times a positive is a negative. And then I'll plug in 6. 6 minus 5, that's positive 1. So that's positive. And then 6 plus 2, that's 8. That's positive. Squared, it stays positive. So this place, a positive times a positive is a net positive. So, a couple of things. What is going on here? What does this mean? What this means is that between negative infinity and -2, for that first segment, your function is always negative. It's always below the x-axis. If you think about this like a function, and we'll see a picture of it down below in just a moment, this expression is always negative for every value less than -2. Between -2 and 5, it is also negative for any value. You plug in 1, it'll be negative. I guarantee it. If you plug in 1, you plug in -1, you plug in -1.999, it'll always be negative. And then from 5 to positive infinity, this expression, without the inequality symbol for a second, that will always be positive, no matter if you plug in 5.01 or 5 billion.01. It will always be positive. So, use your sign chart to solve the inequality. So, if greater than 0, or greater than or equal to 0, choose the positive pieces. If less than 0 or less than or equal to 0, choose the negative pieces, or negative parts. So there's only one part that's positive, and we are a greater than or equal to. We are a greater than or equal to, so we want it to be positive, so we'll circle the only spot that's positive. Yes,
What happens if we plug in -2 and or 5?
into the expression.
Yeah.
Then it becomes 0 is greater than 0, which doesn't make any sense. And that brings up a good point. If these are strict inequalities, so I'm going to say, remember, non-strict implies brackets, and strict implies parentheses. This is a strict inequality, so we cannot include the endpoints, and that makes sense. And I'll explain why in just a moment. So I'm going to actually erase this and make it a little bit more that. So the answer will just be parenthesis 5 to positive infinity. That's the answer. And the reason why we can't include the endpoints, as Ben was noticing, if I plug in 5 into this inequality and see if it solves it, I'll get 0 is greater than 0. Let's actually see that happen. If I try 5, I'll get 5 minus 5 times 5 plus 2 squared. Is that in fact greater than 0? Well, that'll be 0 greater than 0, which doesn't make any sense. 0 is not greater than 0, it's equal to 0. So if we have a greater than or equal to, it can be included. If this was a greater than or equal to, it could be included because it is technically greater than or equal to 0 because it's equal to 0. So if it's a non-strict, you can include it. If it's strict, you cannot include it. Couple things, and unless there's any other questions. Yes, and then you. Did you have a question? Oh, you're just stretch. Okay. Yes.
Yeah, just determine that from the beginning by just looking at the x minus 5.
Why do you say that?
Because it's greater, no matter what, you can't include anything under the.
Well, that has to do, yeah, that happens only because the x plus 2 factor is squared. The x plus 2 factor being squared means that this thing is completely determined by the x minus 5 factor. But that's not always the case, right? It could be x minus 5 times x plus 2, in which case one of those could be positive and one of them could be negative, or both could be negative, or both could be positive.
I was just saying because it's bigger.
No, that's not how it works.
No.
It has to do with specifically the dividing value, the VIPs. Yes.
And the symbol, the greater than 0 symbol also.
Yes. And so I'm gonna actually highlight that in orange.
Should know, so you should pick the positive.
Exactly right. Because we're dealing with a greater than, as Thomas said, because we're dealing with a strictly greater than, we need to choose the positive pieces.
And if we flip the signs, so well,
Yes.
x equals 5.
If this had been less than 0,
then we would have chosen the positive, which makes it negative.
yes, we would have chosen this one, and our answer would have been parenthesis negative infinity to negative 2, parenthesis union negative 2 to 5. We have to use parentheses here because it's non-strict. Negative 2, we don't want to write parenthesis negative infinity to 5 because negative 2 does not solve the inequality because it's strict.
Then why did you union in the positive part? How can we did it in the
Do a union
Yeah.
because it only had one piece. It only had one piece, just that one.
the negatives have 2 pieces. So.
Exactly right. Any other? Oh, go ahead.
Would that change it?
If the negative 5 had been, so like x minus 5 to the third power. Interestingly enough, no, it would not change it. And we'll find out why in just a moment. It's funny that you chose x minus 5 cubed, because x minus 5 cubed has an odd multiplicity. And x plus 2 has an even multiplicity. Maybe something's going on there. We'll find out in just a moment. But one thing I want to bring your attention to, this is far more important than, like, in terms of your homework and in terms of the course, this is more important. But in terms of your understanding of mathematics and moving forward into calculus and stuff, the observation is very, very important. And so what I'm going to say is that the sign chart tells us where the function is above or below the x-axis. So, write that down and I'll explain what I mean. Very, very excited about this. This is one of my favorite parts teaching in Math 126 because I just love doing these and I love the implication. So,
Is the implication.
is very, very useful in understanding graphs. So this is a polynomial x minus 5 times x plus 2 squared. That is the inequality that I'm solving. The left-hand side of this inequality is this function. So in essence, this question here, solve the inequality, is really saying find where the, it's so laggy. There we go.
I like those kids. It's so laggy.
Okay, so I have to like really, really be careful while I'm doing this. So I'm gonna be pointing to the screen. Sorry, people watching the recording. This expression, x minus 5 times x plus 2 squared, if you think of it like a function, then what this inequality, this problem is asking is find where the function
Oh, snap.
let's just,
Yeah, we already kind of found it, remember?
so we'll just change this to a greater than. There we go. Fixed it. Fixed it.
You found it earlier.
I found it earlier when we did it in pink, but either way.
There's a negative 2 union, -2, -5.
Yes. So if you want to solve the other one, the answer, like the original one, the answer would be parenthesis negative infinity to -2 union -2 to 5 with all parentheses. So back to the point. Now that we noticed that mistake. This inequality, this corrected version, is now saying, where is the function x minus 5 times x plus 2 squared? Where is that function positive? Where is it above the x-axis? And so we're actually like the sign chart gives us more information than we actually need, technically speaking. We have to make the sign chart to answer the question, but the sign chart, if I put it like, okay, I'm getting a bunch of things and I want to talk about them all at the same time, and I'm trying to figure out the best way to do it. This function, f of x equals x minus 5 times x plus 2 squared. Based on our knowledge of 2.2, we know how to graph that. That's a degree 3 polynomial with leading coefficient x cubed. X cubed has falling on the left, rising on the right. So we can graph this based on our knowledge of just polynomials, because we know we have a 0 at -2 with multiplicity 2, so it should bounce. And then it has a 0 with multiplicity 1 at 5, so it should cross through. But in particular, if I do that sign chart, I'm going to write it below it. Here's -2, here's 5. We saw that it was negative, negative, plus. That's below, which I'm going to write as a B, below B, and above A. I'd rather use the pluses and the minuses personally because it's more mathy, but if you want to use BBA, whatever it may be, that's fine too. Notice that before -2, you are below the x-axis. Between -2 and 5, you are below the x-axis. And then after 5 is the only part where you're above the x-axis. So the sign chart can tell you that even if you just know the zeros. If you just know the zeros and you have the sign chart, you can figure out what the shape should be even without knowing about multiplicities. This is going to be especially useful when it comes to rational functions, because this will tell us where the rational function would be positive and where a rational function would be negative. And in fact, this could be used for any function in particular. So like as long as we can find the zeros or the roots of the function, we can set up a sign chart and utilize that to figure out what the graph should roughly look like. So that's the nifty fact about it.
You know, the whole sign, like, man, you're not really being the allegation, so you don't know, right?
Yeah,
And also,
up from down.
Bill totally didn't change the sign.
Oh, you wrote that in the thing. I totally didn't change the sign here. Yes, I totally didn't. So that is the implication I want us to understand, is that the sign chart tells us where a function is above or below the x-axis. Because what these plus signs represent is what the sign of the value of the function would be. When we plug in 6, we'll get a positive number. It should be up here. When we plug in 0, we get a negative number, meaning it should be down here. When we plug in x equals -3, regardless of what the number is, it's going to be negative. It's going to be right around there. So the sign chart gives us what the graph should look like. That's what I want us to understand about this. So let's look at this again. Let's do another one. This one, 12x squared is strictly less than 12 plus 10x. So it's not in the proper format yet because not everything is on one side. So I want you to do that. I want you to bring everything to one side, factor it, and find your VIPs. People watching the recording, you should do that too. Very carefully. Okay, so You should get the VIPs negative 2/3 and 3/2. And we're going to ignore what we were talking about during the break. And that just makes people watching the recording more interested in what happened. But anyways, you only get those two. Remember, the 2 doesn't have an X on it. So it doesn't give us any VIPs. If it had been 2X here, then we get 0. But that's not the case. So I've already put a number line here for us. And what we're going to do is we're going to plot our VIPs on it. Oh, and I forgot to explain why this works, and I'll explain why after this. So we'll plot negative 2/3 and positive 3/2. And if you don't know what those know, like especially if they're not nice fractions, they usually are. But if you don't know, you can always use your calculator to find the approximation to figure out what number to test. So negative 2/3, that's negative 6.6 repeating. So I can pick -1. Whenever you have the option to pick -1, 0, or 1, absolutely do it. I'll pick x equals 0 between these two. And then 3/2, that's 1.5. So we could do x equals 2. So this time I'm going to color code it one more time so we can see it in action. I'm going to highlight them this time. 2 is a positive number, so it does not play a role at all. Multiplying by positive numbers never changes the sign. So the 2 doesn't really do anything for us. When I plug in -1, will the blue factor be positive or will it be negative? Negative. Because it'll be 3 times -1, that's -3, plus 2, that's -1. So it's negative. Will the red factor be positive or negative?
Positive.
Careful.
Oh. Yeah, you're right.
It's negative because it's going to be -2 minus a number that's going to stay negative. So you have 2 negatives, that's a net positive. Is that a piece I want? No, because this is a strictly less than. So I'm going to say no, because strictly less than 0. Then we'll plug in 0. Will the blue factor be positive or negative? Positive, because it's going to be 0 plus 2, that's positive. The second factor, the red factor, positive or negative? Negative. So we have a positive times a negative. We have 1 negative overall. That's a net, and that will result in a net negative. And that is a piece that I want. And then I'll plug in 2. Will the blue factor be positive or negative? Positive, because it's going to be 3 times 2, that's 6 plus 2, that's going to be positive. And then the same thing for the red, it's also going to be positive. So this piece will be net positive, and that's a piece that I don't want because I want less than 0 strictly. So my answer is therefore parenthesis -2/3 to positive 3/2. And that's it, parentheses, because it's a strict inequality. If it was a non-strict, I would be able to include those endpoints. Okay. Any questions on that? Besides the overarching thing is why? Why does this work? Yes, Cheyenne.
So all we're doing is like, for example, x equals -1, we're just putting it into like the blue. So it would be 3 times -1 plus 2.
Yes.
And that's how we get our like positive or negative answer.
Exactly right. So to clarify what Cheyenne said, because he's exactly right, what we're doing is we're plugging in this number into each of these factors. And yes, you can find the actual number by doing all the multiplications and calling it good, but it's really not necessary because all we're concerned about is whether it's positive or negative, because we're always bringing the one side of the inequality to be 0, meaning that we only need to know whether it's going to be a positive number or a negative number, because that will ensure that it's either less than 0 or greater than 0. So why does this work? Why am I doing this and why does it work? So they mention it in the textbook, and I don't want to talk about it purely because it's a calculus concept, which is called the intermediate value theorem. Now, the formal statement of the intermediate value theorem is very, very not useful. It's great for a mathematician, not useful in practice. but there's an application of the intermediate value theorem that says that as long as you have a continuous function, and remember, a continuous function, we talked about it in loose terms, it just basically means you can draw it without ever lifting your pencil, which is basically every function that we'll deal with in this course. So this function right here is a continuous function. And so what it says is that as long as your function is continuous, in between your zeros or your places where you don't exist, you will stay on one side of the x-axis. So this is one of our zeros, this is one of our zeros. Do you notice that there is no place in between these two zeros where I'm positive? And that's because if it did have a point up here, then it would have to either not exist here, in which case it wouldn't be continuous, or would have to somehow magically jump and then go back, which it can't do because it only had, that would give it two additional zeros that it doesn't have. So the reason why this works is by the intermediate value theorem, which basically states that the function will always stay on one side of the x-axis in between its zeros. As such, the reason why I bring that up at all, since I know it will always be on one side no matter where I test a value, I can just test one value. And if I know the sign of that value, I know the sign of all the values. So that's why I only tested one here at 0, because I know that 0 is going to be negative. That means that every number in between them is going to be negative. That's what's happening. The intermediate value theorem guarantees that. That's why I'm only testing one number. Is that okay? Any questions on that? Yes, Ariel.
So whether the value of x is negative or positive, that tells us whether the y value, the y-intercept is going to be on the
Above or below the x-axis. In essence, so the x value gets plugged into this expression,
yes.
and whether or not it's positive or negative plays a role in my decision making for what the answer will be. And the reason why I'm only testing one value is because is due to the intermediate value theorem, which will state that as long as I'm in between two zeros, I will always stay on one side of the x-axis. So notice that there's no zeros over here.
Yeah.
So it's always going to be below. It will never magically go back up here, because otherwise it would have to do that, in which case I'd have a new 0 that I never had in the first place. So that's what, yeah. So we're using the x values to determine whether the y values are positive or negative.
Thank you.
Mm-hmm. Any other questions? Ben?
Yeah, this one is asking solve column and column.
Mm-hmm.
Point, I understand the lesson, right? But in this particular question, would we just need to find the x equals -2/3, the x values?
So the x values are only half of the puzzle, because they tell me where it's going to be split up, where it's going to have places that are positive and places that are negative, but they won't tell me specifically which parts are positive or negative. That's where the sign chart comes into play. So the first part is finding where the zeros are. The second part is the sign chart, and that's finding where the pieces are positive or negative. Is that all right?
Yeah, what would differentiate this from other things that we've done in the past, though? How would we know to do
This setup?
this setup compared to just solving normally? Because if I see solve column.
Oh, okay.
Nothing is indicating that I need to.
So the thing that is indicating a number line, there are two things. The word portion, the English portion, is the fact that it says inequalities. Inequalities don't behave exactly like equations, because an equation only has equality. And so there are only two answers. If this was saying solve this, there's only two answers. And there's no need to find solve an inequality, because there's only two instances where you're actually equal to 0. The mathematical thing that tells you need to make a sign chart is that less than or equal to sign. As soon as you see an inequality symbol, whether it be less than or equal to, greater than or equal to, you need to make a number line. And that is because equalities can only have equal, whereas inequalities there are infinitely many numbers that are less than zero. There are infinitely many numbers that will solve that inequality. Hence the reason why we get interval notation and not just two numbers. Yes. Yes.
So the opposite of this answer would be negative infinity to negative 2/3 union, 3 seconds to positive.
That's correct. So if this question had instead been this, then the answer would be negative infinity to negative 2/3 parenthesis union parenthesis 3/2 to positive infinity. So we can even add that as an aside. So if 2 times 3x plus 2 times 2x minus 3 less than 0, if that was the question, then that would be the answer. So point being is that the direction of the inequality decides what the answer should be. Yep. Sorry.
Started doing it and I looked up and I was like, what do you mean?
Yes. There we go. Thank you. Thank you. Okay. Other questions? Any other ones? Yes.
This might be extra, but can you like draw that as a graph?
Sure. So the graph of this function, that's a quadratic. This right here is a quadratic function. In particular, it's a quadratic function with zeros at negative 2/3 and 3/2. Now, this is good practice for the upcoming exam. Is that parabola going to, if you're looking at this function as a parabola, so y equals 12x squared minus 10x minus 12, which is 2 times 3x plus 2 times 2x minus 3. Is that an upward facing parabola or a downward facing parabola? Upward, because its a value is 12, which is positive. And so if your a value is positive, you're an upward facing parabola. So the graph of this looks like this. Here's negative 2/3. Here's 3/2. And this parabola will look something like this. And notice that the places where it's greater than 0 are precisely these two intervals. And the place where it's less than 0 is precisely this interval while you're below the x-axis. So that's a good thing to like, and I'm glad you brought that up because that really will help us once we start talking about how to graph a rational function without using test points. Is that okay? All right. I would like you guys to now do this whole problem here. And notice that this is a non-strict inequality this time. It's a greater than or equal to. So go ahead. That means to set it equal to 0. So bring everything to one side, factor it, find the VIPs, and create the sign chart to find the answer. So people watching the recording, you should do that as well. If you're stumped, unpause it and I'll give you a hint. Here is the first setup hint. Here is the number line, which is the second part, and now we'll work on our answer. Right, and here is the answer, but this is what John Doe student has boxed in as their answer, and I'm going to mark them off one point and say, simplify it, and I'll give you full credit back. Because 0 is included here, we can combine these. So the answer should be -5 bracket to positive infinity only. We can simplify this because 0 was included in at least one of them, then the whole thing is there. And you can see that by the graph that I've drawn below. If we're asking for all the numbers where it's greater than or equal to 0, that corresponds to up here, but it also gives me the spots where it's equal to 0. Because it can equal to 0 with this non-strict inequality. So in essence, sorry, people watching the recording, it'll go from -5 all the way onwards because because 0 can be included. It does solve the inequality. Yes.
And just to clarify, it's going through and bouncing because of the multiplicity, right?
That's correct.
First one is our -5. The 3x cubed is -5.
Mhm.
Okay.
And that's going to cross through because that's multiplicity 1. It's really, really cool that you guys are noticing that because that actually is a way to solve these maybe a little bit faster if you want to, without having to test values. It's a cool way to do it. It's just another way, but I want to talk about it because it's clever. All right. Any other questions? So don't panic though on an exam if you write that as your answer. Because once again, this is a situation where I would mark off 1 point, but I'd let you know, I'd say simplify it and I'll give full credit back. Because you did everything correctly. It was just a minor inconvenience that you didn't notice about while you're working through an exam in a stressful time period. Any questions?
Yeah, you're almost good.
You're almost there, bro. Yes. That's what it needs to be. Okay. So this one is, I want to do this one together because this one is new. This one is a rational function that we're trying to solve the inequality for. So it's the same thing though. We're going to factor it as much as possible. Luckily, one side is already 0. So we don't need to bring anything over. We just need to factor it. So this becomes x plus 2 times x minus 2 over x minus 3 is greater than or equal to 0. So the VIPs are x equals -2, +2, and +3. But I'm going to highlight 3. The problematic VIP. And we'll explain this, we'll explain why once again in a moment. For right now, the reason it's a problematic VIP is because it cannot be plugged into the expression, into the inequality. If I try and plug in 3, I'll get undefined is greater than 0, which doesn't make any sense. How can an undefined quantity be greater than 0? We don't know what the quantity, like it's undefined. It doesn't exist. How can not exist be greater than 0? Answer, it can't. Doesn't make any sense. So I do this to remind myself that it does not exist. Now that we've found the VIPs, we'll set up our sign chart. And so setting it up in order, -2, +2, and 3, and I'm going to highlight the 3. Or underline it, or box it, or I've had students do all types of things in the past. I've had students do this. Like they box it in with numbers. I've had students do like sparkles to mention that it doesn't that like it's important to look at. I've seen students cross it out for themselves. Any of those things is possible. I'm just going to highlight it. So we'll do test values in between. So let's do x equals -3, x equals 0. Oh no, there's no nice integer between 2 and 3. That's okay. That's okay. You can choose any number. So you could do x, like the tradition is to just find the halfway point, 2.5. That'll work. But if you want to, you can do 2.000000001. Any of those things will work as long as it's any number in between 2 and 3. Yes.
Are we allowed to use like decimals, or do we turn it into a fraction?
You can use decimals because this is for us to check. I know Alex sometimes has problems with decimals, but this is for us to work through. So we can use decimals if we want. And then a number greater than 3, let's do x equals 4. So I'm not going to color code it anymore, but basically we're going to be plugging in those numbers into the factors and seeing whether they're positive or negative. So the first one, if you plug in -3, it'll be negative times a negative over a negative. Because -3 plus 2, that's -1, that's negative. -3 minus 2, that's definitely negative. -3 minus 3, that's taking a negative and subtracting something for it. Of course, it's going to be negative. So we have a net we have 3 negatives, which is a net negative, right? 2 in the negatives will cancel out. You can always pair up 2 negatives, but you're going to have 1 negative left over, resulting in a negative. That is not a piece I want because I want the pieces to be strictly greater than 0 or greater than or equal to 0. Plug in 0. I should get positive, negative, negative. Positive times a negative over a negative. That's 2 negatives total. That's an even number of negatives. They will cancel each other out, resulting in a net positive. That is a piece that I want. Does anybody have any questions on that one? I do this in the exact order that I see it. Because I wrote x plus 2 times x minus 2, the first factor, the top left factor will be positive because 0 plus 2 is positive, 0 minus 2 is negative, and 0 minus 3 is negative. Next one, 2.5. The first one will be positive. The second factor will now be positive, and then the factor in the denominator will remain negative because it'll be negative 0.5. So that's a total of 1 negative. That's a net negative. That's a piece I don't want. And then, last but not least, if I plug in 4, all of the factors will be positive. And that's a piece I want. Couple things. I've deliberately catered these problems. I chose these ones very, very specifically. Do you notice that this one, it didn't go positive, negative, positive, negative. It doesn't like it didn't flip-flop. This one did, this one didn't. And that's because I like a common mistake that I see students make is they assume that once they find the first one, they can just keep alternating because Alex usually likes to throw ones that are always multiplicity ones for all the factors, which will make it flip-flop each time. But don't assume that. Don't assume that it always flip-flops. Sometimes it does, sometimes it doesn't. So you have to test it no matter what. Don't just assume that the next one's going to be the opposite side. Okay, so we have our pieces. And so the answer I'm going to tell you is bracket -2 to +2 bracket, because this is a non-strict inequality, so endpoints should be included, except for 3. Union parenthesis 3 to positive infinity. That is our answer. Not bracket 3, but parenthesis 3. And why is that? I said it earlier. Hopefully people remember.
Because the 3 is problematic.
The 3 is problematic. In particular, so we'll put an explanation here. 3 cannot be included, even though this is a non-strict inequality. This is a greater than or equal to. But notice that if you like, at the end of the day, what we're trying to do is make sure that the numbers inside these intervals solve the inequality. Now, -2 can be plugged in, because if you plug in -2, you'll get 0 divided by -1, or sorry, by 0 divided by -5, that's 0, and 0 is in fact greater than or equal to 0. You plug in 2, you'll get 0 over -1, that's 0, that solves the inequality. You plug in any number in between these, it will solve the inequality. You plug in any number between 3 and infinity, it will solve the inequality. But as soon as you try and plug in 3, because then we get 3 squared minus 4 over 3 minus 3. Is that greater than or equal to 0? Well, that's undefined. Sorry, let's do one more step before writing that. That's 9 minus 4, that's 5 divided by 0. Is that greater than 0? Undefined. Is undefined greater than or equal to 0? And that's ridiculous. So that's the reason why. Ariel, yes.
Going forward, is it always gonna be like this when the problematic value is the one that is like on the denominator side? When it comes to these inequalities?
Yeah, the problematic inequality, the problematic VIPs will always come from the denominator.
Okay, so when we plug in, if it happens to be the always the strict parentheses when it comes to.
With problematic
I don't know how to
VIPs,
do
yes.
it.
No.
Yeah.
So like, make sure I'm saying it right. So when it comes to problematic VIPs, they are always parenthesed.
Okay.
And so this brings up another good point. You only really have to worry about this scenario when you're dealing with non-strict inequalities, because in non-strict inequalities, you have to worry about whether or not you can include an endpoint.
Yeah.
But if this was a strict inequality, if this was like this only, then all of these would be parentheses and you wouldn't have to worry about whether or not to plug it in. And I know you had a question, I'll get to it in just a second. So the non-strict inequalities are always the ones you need to be a little bit extra careful about, because problematic VIPs cause problems. Oh, you got a question?
So since it was greater than or equal to 0, when we're doing the top portion,
Mhm.
should we be checking if it equals 0 or just following the simple, it's negative or it's positive?
So that's a good question. And the answer is usually you just follow the signs. There are a few cases, as you'll see, these ones, the dreaded curly brace case. And that is a situation we'll talk about afterwards. And that is one where we do have to worry about the numbers in particular, but we'll get to that. This one. So this one right here, unless there's any other questions on that one. These are great questions, by the way, guys. Okay. This one. Problem is, it's not 0 on one side. So we either need to bring everything to the left or everything to the right. I did that opposite, but it doesn't matter. I did that opposite with my hands. Now, it's going to be better. It's going to be better for us to bring it all to the right-hand side, technically speaking, but I don't want to do that because I want to illustrate a point that will happen very often for you. So we're going to bring everything to the left. Yeah. So we've got 3x, just 3 over x plus 3 minus, leave a little bit of space and then write the minus sign, 6 over 2x plus 1 is less than or equal to 0. Oh, actually, leave a little bit of space after the before the less than or equal to sign, like that. So we've already got everything on one side. That's good, but we can't factor it right now. So what should we do? As soon as I see an inequality, as soon as I see two fractions, common denominator. Common denominator. So we need to multiply this fraction by 2x plus 1 over 2x plus 1, because the LCD here is x plus 3 times 2x plus 1. Remember, the LCD is the collection of all the prime factors raised to the highest power that you see. So x plus 3 is a prime factor, 2x plus 1 is a prime factor. They're both being raised to the first power. If this had instead been x plus 3 squared, we put an x plus 3 squared there in the LCD, but it's not. So then to combine the common, to get a common denominator, all we need to do is multiply each fraction by what it's missing from the LCD. So the first fraction is missing the 2x plus 1 factor. The second fraction is missing the x plus 3 factor. Doing so will give us 6x plus 3 minus, parentheses, 6x plus 18 divided by x plus 3 times 2x plus 1 is less than or equal to 0. And feel free to skip as much algebra as you feel comfortable. So if you wanted to distribute the minus sign in from the start, that's your call. But I like to simplify them and then combine them. The reason why I've already drawn them all over the same fraction is because by doing what I've done in red and green, I have guaranteed that these things have the same common denominator. Even though they're in reverse order, right? This fraction has it as x plus 3 times 2x plus 1, whereas this one has 2x plus 1 times x plus 3. But remember, multiplication is commutative, so it doesn't matter which factor shows up first. Ben.
Are we not keeping it factored?
Because right now it's not actually factored. They're in parentheses, but that's not multiplication in between them. That's subtraction. So I need to distribute the subtraction so that I can then factor it further. Does that make sense? Let me say that.
Wouldn't you just end up with the same thing?
Not exactly.
Multiply it?
If you multiply, you won't get the same thing. You have to distribute the minus sign. I understand what you're saying, like the idea, but if it was multiplied, then leave it as is. But it's not multiplication, it's subtraction. So it has to be that subtraction needs to get distributed and everything needs to be taken care of that way. So we get 6x plus 3 minus 6x minus 18 divided by x plus 3 times 2x plus 1 is less than or equal to 0. The 6x's will cancel, and we'll get negative 15 over x plus 3 times 2x plus 1 is less than or equal to 0. Any questions so far? Any other questions so far? Okay. So now that we've got it to be factored and all things on one side so that the other side is 0, we can find our VIPs by setting all the factors equal to 0. The VIPs are x equals negative 3 and negative 1/2, but they are both problematic. Because they make the denominator equal to 0. So they can't be included in the calculation. Even though this is a non-strict inequality, if we find an interval that has that as an endpoint, we cannot include it because it makes the expression become undefined is less than 0, or undefined is less than or equal to 0, which doesn't make any sense. So we found our VIPs. Let's go ahead and plot those on the number line. Negative 3 is more negative. So we're at negative 3 and then negative 1/2. And then we've got to use some test values. So a number less than negative 3, negative 4 is fine. A number in between negative 3 and negative 1/2, negative 1 will work. And then a number greater than negative 1/2, 0 is a great choice. 1 is also a good choice. However, before I continue, this is different than this case up above. This first case that we did, where it was positive 2. A positive number has no bearing on the sign. But notice that this one has a negative 15, which I'm going to highlight in green. Specifically, this. Plays a role in the sign chart. So I know that negative 15 is always going to show up. So I'm going to put a negative sign in the numerator each time. If it was a positive number, we just write a positive. But that negative number, remember, the number of negatives in a product or quotient will help decide the sign. Then, any questions on that? So be careful with those negative numbers. They play a role. Any negative coefficients play a role. Any positive coefficients don't, because they don't change sign. Only negative numbers do. Then we'll plug in these numbers. The denominator in the first subset where we're testing negative 4, that'll be a negative times a negative. That's 3 negatives, so that's a net negative. And that's a piece that I want because I want to be less than or equal to 0. I forgot to do something. I forgot to highlight my problematic VIPs. It's something I've forgotten over the years because I'm so used to it. I've done it so many times that I know to already check for it. But either way, I'm going to highlight them. When I plug in -1, it'll become positive times a negative. So that's 2 negatives. That's a net positive. And then if I plug in 0, I'll get a positive times a positive in the denominator. That's 1 negative. That's a net negative, and that's a piece that I want. So but these are both problematic VIPs. If you try and plug them into either our simplified version at the very bottom or the original version, you plug in -3, you'll get undefined is less than or equal to something. That doesn't make any sense. And if you plug in 1/2, you'll get something is less than or equal to undefined, which also doesn't make sense. So we cannot include those things. So the answer, even though this is a non-strict inequality, there will be no brackets. This will be parenthesis -infinity to -3 union -1/2 to positive infinity. And you can add that comment if you'd like. Because they make the expressions in the inequality undefined. Okay? Any questions on that?
Is that because you don't get, anything -3 or -1/2?
Say it again.
Once you do the problem, right, you don't get, x equals like 3.
Yeah, you won't, well, x equals 3 is fine. But -3 can't be
You
plugged
get
in.
the equal to, I'm sorry, you don't get the equal.
Exactly. Well, it's more than you don't get the equal to, you get undefined.
Okay.
If we ended up getting a factor in the numerator, we would have some brackets involved because the numerator could be 0 and that's okay. Good?
So the reason why there's no. So there's no bracket. Even though it's like greater than or equal to.
Even though it's a greater than or equal to, because those are problematic VIPs, they make the expression undefined. They cannot be included. And I forgot to do it on the previous one, but this is what the function will look like, actually. -3, -1/2. And so my sign chart actually tells me what this should look like. It should be negative before -3. So this piece needs to go like this. And there's also a horizontal asymptote at y equals 0. And then between -3 and -1/2, it's positive based on my sign chart. So it should look like this. It can't go negative, so it has to hug the asymptotes. So it has to go down and then immediately come back up without ever hitting it. And then after -1/2, it's negative again. So it has to stay below the x-axis. So we can graph these things very quickly by looking at the sign chart. Did you know I didn't have to plug in any numbers? Isn't that great? Way faster. So we'll see how to do this in a little bit, but that's how you do it. You know where the vertical asymptotes are, and I could even do it with this one too. In fact, maybe during the break, I'll do that, but we're going to take a break. We'll come back at 11:51. Say what?
You just follow.
That's correct. Yes, before we go on our break, I'm following the chart. Where the negative pieces are, my function will be below the x-axis. Where the pieces are positive, I'll be above the x-axis. This graph? Yes, real quick. I know that, so I did this. This is something we'll talk about in more detail, but this function has no x-intercepts because the numerator is just a constant. So setting the numerator equal to 0 won't give me any x-intercepts. It will have a y-intercept. I don't know what it is, but I can just plug in 0. But it has 2 vertical asymptotes, one at -3, one at -1/2. So that's where I've drawn those. And because the degree of the denominator is 2 and the degree of the numerator is 0, it has a horizontal asymptote at y equals 0. And then I'm using, like, the rest of it is using the sign chart. Before -3, it has to be negative. It has to be below the x-axis. And since it has to hug its asymptotes, I know it should look like that. There's no way for it to be drawn up here because that would mean that the graph would be positive up there, but our sign chart tells us otherwise. Then between -3/2 and -1/2, we have to start either, when you're talking about a rational function, it either has to start here because it has to hug its asymptotes, or it has to start up here. But because it's positive, the only option is for it to be up here, but it has to stay positive, so it has to go down and then come back up. And then last piece, it has to be negative, so it has to stay below the x-axis, and that's where I get that. That's how that happens. Of course. So let's come back at 11:52, and we'll continue then. People watching recording, do some guided meditation and some sit-ups. Okay, so during the break, oh, Darren, yes.
What causes brackets and color?
So brackets have to do with included versus excluded. If it's included, it's a bracket. And if it's excluded, it means that it's a strict inequality. Or it's either a strict inequality or it can't be included because it makes the denominator undefined.
Oh,
So during the break, I drew the graph of what this one should look like. It has one vertical asymptote at 3, and then the degree of the numerator is 1 more than the degree of the denominator, meaning it has an oblique or a slant asymptote, which is where I've done here. I've done the synthetic division, and I got y equals x plus 3. That's how I drew this line. And then the numerator gives me the x-intercepts, -2 and 2. And then I use the sign chart to do the rest of it. From -infinity to -2, it's below the x-axis. From between -2 and 2, it's positive, but it has to come back somehow so it can hug this vertical asymptote. And then from 2 to 3, it's negative, so it has to go down towards this. Then from 3 onwards, it has to be positive, but you might be saying, well, Phil, it's also positive here. But if it were to do that, I'm going to draw that in purple. If it were to do that, then it would have to hug the asymptote down here. And that would make it go negative, which it can't be because it has to be positive. So that's how you can use a sign chart to make this quickly. That's the nifty trick. So I will leave that up here for a second and we'll start working on the next one. So this is a nice little way to do it by using the trick. Negative means below the x-axis, positive means above the x-axis. And there you have it. Very, very quick way to do things. Is it okay if I move away from this, or are people still writing it? I think people are still writing it. No? Okay. If you need it, let me know and I can bring it back during the break or when we leave. So this next one, I'd like you guys to start working on this one. Notice that the right-hand side is not 0, so you will need to bring it over and then do something else to figure it out. So people watching the recording, go ahead and start working through it. Here's the first step if you're stumped. This is the next step to help you out. And here's the sign chart. And then we'll get our answer. And this is our answer, so we'll go through it once again. So we got to bring everything to one side because you need one side to be 0. That way you can check sign instead of trying to find out if it's greater than a specific number or not, which is much more challenging to work with. So when you do that, you get 2x squared plus 3x minus 4 over x plus 1 minus 2, but that can't be solved, that can't be factored yet because you need a common denominator. The common denominator here being x plus 1. So I'll multiply the 2 by what it's missing, which is the x plus 1 over x plus 1. Doing the algebra to simplify, that brings you down to 2x minus 3 times x plus 2, all divided by x plus 1, is less than or equal to 0 in the very, very bottom. By just doing some algebras. That gives me the VIPs 3/2, -2, and -1, with -1 being a problematic VIP because it makes the denominator equal to 0, and you can't divide by 0. Then we make our sign chart. The only thing of real consequence that's confusing is the fact that we have -2 to -1, so there's no nice integer between those two. So I just chose -1.5, but there's nothing stopping you from doing -1.75 or -1.1 or anything like that. And you get negative, like the two pieces that are negative are from -infinity to -2 and from -1 to 3/2. We put brackets on the -2 and the 3/2 because they are places that will solve the inequality. You'll get, if you plug it into the original inequality, you will get 2 is less than or equal to 2, which is a true statement. But as soon as you try and plug in -1, you'd be dividing by 0, and that's a big no-no. That's why that one has a parenthesis, whereas the other ones don't. Any questions on that? Okay. So we'll do this next one together. Oh, Ben. Yes.
When do we start factoring the top one?
Once everything has been simplified.
You just gotta combine everything first and then do it.
Exactly right. Oh, yes. So now, luckily for part B, everything's already factored for us. That's excellent. So we don't need to worry about it too much. We already know what our VIPs will be. Our VIPs. Is it okay if, or no, you're still working, So yeah, take your time. Since it's already factored, the VIPs are right in front of us, which is excellent. That's a nice thing about this one. So this one's trying to tell you that the difficulty is in the setup of the sign chart and in the final answer. Good news for us is this is strict inequality, so we don't need to worry about including endpoints. So we don't need to worry about problematic VIPs in the long run, but it's still good practice to do so. So we have the VIPs are x equals -5, x equals 1, 0, and -3, with 0 and -3 being problematic. Let's plot all those on a number line. Quite a few. You got 4 of them total. So -5, then -3, then 0, then 1, with 0 and -3 being problematic. Once again, because this is a strict inequality, that's not going to matter too much, but doesn't hurt to still mention it. And then we need to just pick some test values. X equals -6, x equals -4, x equals -1, x equals 0.5, and x equals 2. So once you've set up the sign chart like that, I want to talk about something real quick. It happened during the break, and I think we should mention it again. Remember that any factor raised to an even power is always positive. X squared is always positive. X to the 4th is always positive. X plus 5 to the 200th is always positive because of that even power. It'll give you a bunch of like if the inside's negative, you'll have an even number of negatives, which will result in a net positive. So those things are always positive. The even powers, it's the odd powers that cause changes in sign. And that has to do with multiplicity as well, but we'll get there. So -5, it's x plus 5 to the 4th, so that one's always positive. So I'm going to just go ahead and put that one as always positive so I don't get tripped up and make a mistake. And the same thing goes for the x squared in the denominator. That thing is always positive because if you plug in -6, -6 quantity squared is positive 36. -4 squared is positive 16. -1 squared is positive 1. So that thing is always positive in the denominator as well. And then the other two factors, the x minus 1 that's being raised to the first power, so sign does matter there. And then x plus 3 to the third power, that will always keep its sign because it's an odd power of x. It's an odd power. So -6, that'll be negative. -6 plus 3, that's also negative. So that piece is positive. That's a piece that I want. When I plug in -4, that'll be negative. And -4 plus 3, that's -1. That's also negative. So this is positive. That's another piece that I want. -1. It'll be negative up top, but now it will be positive. So that's a negative. That's a piece I don't want. 0.5, that'll be negative. And 0.5 plus 3, that's positive. So that's negative. That's a piece I don't want. And then when I plug in 2, they're all positives. And that's a piece that I want. This is a strict inequality, so none of the endpoints will be included. So it's going to be 3 intervals, all unioned, all with parentheses. So it's going to be parenthesis -infinity to -5 parenthesis, union parenthesis -5 to -3 parenthesis, union parenthesis 1 to positive infinity parenthesis. So in the interest of time, I'm going to skip the multiplicity trick. I'll keep that up here for a second. We're still writing. Jump down. The multiplicity trick is pretty nifty. You still need to test one value on the left-hand side, but then you can use multiplicity to figure it out. We know with a multiplicity of even, like -5 has, it'll bounce. So it'll stay positive. It'll stay on one side of the x-axis, whereas -3 has a multiplicity of 3. It's odd. So it should flip, and it does. Then it's 0, that's an even multiplicity, so it stays the same. It bounces and stays where it was. And then at 1, we have a multiplicity of 1 that's odd, so it flips and changes. So you can bypass a little bit of testing. It saves you maybe 20 seconds, maybe 20 seconds. So it's not that big of a deal, so that's why I'm going to skip it. But if we have time, we'll check that out. Okay? Ariel, yes.
We never joined the we never joined the what was it again?
The union.
The unions when it's strict inequalities, right? We only do it when it's the non-strict ones.
Exactly right. So that's these two right here cannot be combined because -5 is not included in either of the pieces. Whereas in this, so if it had been this, then you could union them together. And it would and then it would be -infinity to -3 like that. But that's only because as long as one of them has -5, it can be included in both. But as it stands, these are both parentheses, so it cannot work.
Thank you.
It's for the points or the unities of from 0 to 1. The 0 is not included, but you don't put it into the solved amount is because it's negative?
Yes, because those pieces are negative and we want to be strictly greater than 0. Okay, so we'll skip this page for now. If we have time tomorrow or on Thursday, we'll come back to it. But I want to get to Tom.
How do you know which sides will be?
Oh, that's based on the net number of negatives that you have, the total number of negatives. So yeah, if there's 2 negatives, they'll both cancel each other's negative signs out. If there's 1 negative, then the whole thing will be negative. Is that?
Which one's exactly top?
Oh, how do I know? So I'm plugging it into each factor. So I'm kind of doing a quick algebra arithmetic calculation in my head. -6 plus 5 is negative, but this is being raised to the 4th power. And even powers always make the things positive. So when we were doing this one, I just put the positive sign in all of them from the start because I knew that this factor was always positive. Same thing with the x squared. It's always positive. But the other ones, they do get affected by sign because they are odd multiplicities. And that makes them, like -2 cubed is -8. So odd powers keep the sign that they have. Even powers always make things positive. The multiplicities, the exponents. This is an exponent of 1. This is an exponent of 3. So the exponents are what's playing a role here.
It was kind of fun, just too many steps.
So what?
It's kind of fun,
I'm glad you think so.
pretty fun, but I just like these too many steps.
Sometimes it is, especially with a lot of zeros. So let's circle back then in just a moment, okay?
Yeah.
Yeah. So, to Connor's point, do I need to worry about the end cases? The dreaded curly brace. You'll see this and it'll make you very angry on Alex because it is such a minor nuance, but it is important to understand. The thing is, much like with the exclusions of problematic VIPs, this only happens when you have non-strict inequalities. Strict inequalities, you never have to worry about this. And it's because 0 is less than or equal to 0 and 0 is greater than or equal to 0 are technically true statements. So let's go through this one. X to the 4th minus 6x cubed minus 15x squared plus 8x greater than or equal to negative 4x cubed plus 8x. So everything can be brought to one side. That's what we need to do from the start. So we need to combine everything. So this is x to the 4th. I'm going to skip a little bit of algebra. I need to add 4x cubed to both sides. That's going to give me a minus 2x squared. Or 2x cubed, excuse me. Then I have a minus 15x squared. And then I have a positive 8x minus an 8x. Those cancel out. So this is what I have. X to the 4th minus 2x cubed minus 15x squared. There's a common factor of x squared that can be pulled out front. So we'll factor that out. And then we've got x squared minus 2x minus 15 is greater than or equal to 0. And then that factors nicely to x squared times x minus 5 times x plus 3 is greater than or equal to 0. So the good news with this dreaded curly brace case is it's the same process. And if this was on an exam, I try to avoid having this on an exam. It's mainly just a homework exercise to notice. But if it were to show up this like, and you forgot to include the curly brace, it'd be a 1-point deduction if that. And then that means that it's only worth half a point once you do the redo. So Ben, did you have a question?
Yeah, what do you mean by the curly brace?
So we'll see that just when we get the answer. So the VIPs, sorry, Ali, did you have a question? Okay. Are x equals 0, 5, and negative 3. Let's plot those on our number line. And none of those are problematic because we're not dividing by 0 ever, because this is just a polynomial inequality. So negative 3, 0, and 5. And we'll pick some test values. X equals negative 4, x equals negative 1, x equals 1, and x equals 6. So before I even start testing these values, I'm just going to remind us again, x squared, the first factor in that factorization of our polynomial, it's always positive. So you don't even need to really worry about it. You can just put it on from the start that it's always going to be positive, no matter what. It doesn't hurt to work sequentially, but just so that it's already taken care of. Plugging in negative 4. So I'm plugging in negative 4 into this factor, and that'll be negative 9. So that's negative. And then if I plug in negative 4 into the third factor, it'll be negative 1. So that's negative. And so that's 2 negatives. That's a net positive. That is a piece that I want because I want to be greater than or equal to 0. Negative 1, the x minus 5 factor will be negative, but the x plus 3 factor will now be positive. So that's a net negative. That's not a piece that I want. Then at 1, the x minus 5 is still negative, and the x plus 3 will be positive, so it's negative here. That's a piece that I don't want. And then at 6, both of them will be positive, so that's a net positive, and that's a piece that I want. So John Doe student writes the answer as negative infinity to -3 bracket union bracket 5 to positive infinity. Don't write this. This is not correct, technically speaking. I mean, you can actually fix it at the end. So that is almost all of it. And if this was on the exam, if I accidentally put a dreaded curly brace case on there, I'd give this a 9 out of 10, maybe even a 9.5, so that when you get the redo, you'd get a 0.25 off, and that's it. Because it's a really annoying thing. The answer is actually union curly brace 0. And the reason why, even though the interval from -3 to 0 is not positive, and same thing for 0 to 5, 0 still solves the inequality. Note that 0 still solves the inequality. We get 0 is greater than or equal to 0. So when you plug in 0 into the inequality, you get 0 on the left side, you get 0 on the right-hand side, and you have a true statement. So even though the intervals don't work, the 0 still does. And that's because this is a non-strict inequality. So if you're looking at the graph of this function, what it looks like, here is -3, here is 5. What the curve will look like is it'll go, that's a cubic, right? Wait, no, that's a quartic. That's a quartic. So it'll go like this, like that, and then like that. So you have this piece over here that should be included. That's the piece from 5 to positive infinity. You have the piece from negative infinity to -3. That piece is included, but this is a non-strict inequality. So any place that's also equal to 0 should be included, which is this individual spot right there. It's annoying. It's a really, like, it's a technically correct situation. And that's why I dislike it. And it's one of those things, like, you've done all the stuff and you just forgot to test that one extra point. So I don't really like, I can tell you, I will do everything in my power to make sure that type of situation does not show up on the exam. If it does, I will let you know that there is a dreaded curly brace situation, but that's it.
So generally you would try not to have this.
Yeah, so Alex may have it on occasion, but it's, oh my God, we're already over time. I'm sorry about that. Ben, yes.
If -3 is included, why don't we just write negative infinity to 0?
Because the snippet from -3 to 0 is all negatives. So this snippet right here in red is negative, so it doesn't solve it.
Oh, and we're just trying to find what does solve it.
Yes.
Okay.
Yep. Sorry to keep you guys late. If you have any questions, please feel free to email me. Otherwise, Ariel, did you have a
When
question?
it comes to like whole number with no division, no denominator, no numerator, the 0 always solves the equation.
Mhm.
Then-
It will, if it's a non-strict inequality, yes.
Okay, and is it okay also if I put the 0 in between the
Yes.
both?
I would prefer, like, me, just my small OCD tendencies would like this to be like this.
Yeah, that's why I asked because
Yes.
he also might.
It makes more sense on a number line, but I would accept either, because I usually see it the most common way. I see it like that, even for myself, because I'm like, oh yeah, I needed to test that.
Would you rather be in the middle, right?
Technically speaking, yes.
Thank you.
All right, guys.
Have a nice day.
See you later.